Okay, let's solve this question together. Let's read it first. A uniform beam of length 20 cm is balanced on a pivot at its center. Okay, so this is the beam. We have it as a uniform one, which means that at each point along this beam is as heavy as each other, so it's uniformly distributed along the beam. Next, it had a length of 20 centimeter. Okay, good. So we got some numerical values here that maybe we can apply to solve for the answer later. So keep it in mind, this is the length from one end of the beam to the other end of the beam. And this is balanced on a pivot at its center. Okay, so this is the center of the beam as well. So it also indicates that this is the middle of this length. So then we can know that the length of each part here, right? Good. Next, a 20 Newton load is placed at one end of the beam. Okay, so this one end. We have 20 newtons here, okay? And another 30 load is placed at the other end here, okay? Then we add another load of 25 Newton is also placed on the beam to balance it. Okay, got it. How far from the pivot is the 25 Newton load placed? Okay, interesting. So this is a balancing problem. It's talking about a uniform beam. So we can recall that in order for some object to stay balanced, we need the total moment acting on it should be zero. It means that the total moment that can rotate the beam clockwise here should balance out with the total moment that can rotate the beam counterclockwise. So then everything can be cancelled out and then the total moment can be zero. So basically we need to identify on the moment that presented in here and identify which one can rotate the beam clockwise and which one can rotate the beam counterclockwise, and then we need them to balance each other out. Okay, so what is a moment? If you can recall, this is the definition of the moment of a force. It equals to the force times with the lever arm. So what is the lever arm or the lever arms again? Let's just have a recall here. For example, if this is the beam, just an example, right? So if we have some force in this way, I just want to draw a really random force, okay? And then we can want to see how the effect of rotation that this force can apply to this beam. The moment. Then first, we need to identify the line of action, okay? This is the first step. What is the line of action? Basically, if this is the direction of the force, then you have another line that contains the vector force itself. That would be the line of action. It means that the force will act on the subject along this line, okay? So that's the line of action. Next, how can we identify the lever arm? Okay, so then you need to identify the pivot point. It means that the points that around that point, the object will rotate, okay? Then next, you find the distance from the pivot to the line of action. So as a distance, it means that is a segment from the pivot down to the line of action, and it should be perpendicular to this one, okay? So it should be perpendicular like this, okay? So this will be the, let me move it correctly here, okay? So this will be from the pivot point down to the lines of actions here, 90 degrees at a right angle. Then this one will be the distance from the pivot down to the line of action, and that's the lever arm. Make sense? Okay, so now let's apply this concept to solve this problem here. We have a 20 Newton load placed at one end of the beam. So we have two ends of the beam, one here and another one here. We can pick any, right? 20 newtons can either be on the left or on the right. So imagine if we put some heavy stuff here, like 20 newtons. So because of the weight of the load, it should like press the beam down, right? And we can imagine that it's just like this. It means that it will apply a force on the beam this way. And because of its weight of the load, so then it will be point straight down. So it's just a vertical downward direction. Do you agree? Right? So what is the line of action? It's just a vertical line, right? Downward, right? It's a vertical line. Now, next, pivot point. Where is the pivot point? Here. This is the pivot point here. We need to draw from the pivot point down to the line of action. Okay, so now you can see we want the beam to be balanced, right? So in this situation, in this contact, can you see that? This one turns out to be the lever arms, right? From the pivot point down here. Because this one is perpendicular itself, right? It's horizontal. And horizontal is at right angle to the vertical. So then this one turns out to be the lever arm D1 of the force F1. Do you agree? So can you find D1? D1 just like 10 centimeter, right? Half of the length of the beam, right? Because this is the midpoint, the center. And then what is F1 here? F1 is just like 20 Newton, right? So see, we got the moment of the F1. And what is the tendency of this moment? Could it rotate the beam clockwise or counterclockwise? In these directions, right? Okay, so if it's in this direction, it should be a counterclockwise, right? Okay, so then we leave it on the left side then. Next, you can try with the 30 newtons, right? Here we have another load, 30 newtons. Because it's heavier than that one, so the force is like longer, right? The vector force is longer. Let's say this one is like F2, okay? And then again, the distance from the pivot down to the line of action with also a vertical line, right? Again, it's the same distance, right? Because this is the middle point. So this is D2. Then D2 also turns out to be 10 centimeter. Do you agree? Then we have F2 here times with D2. Then F2 is like 30 newtons here, right? So then this is the moment of F2 that can cause the beam to rotate this way, right? So it's a clockwise. Okay. So now we have this one have the tendency to make it rotate clockwise. This one is like counterclockwise. So let's just do some math here. 30 times 10, 300 newtons centimeter. Then this one here is like 200 newtons centimeter, right? Okay, can you see something here? We got this one 200, this one 300. So basically, are they balance each other out now? No, not yet, right? This one is larger. So in order for this one to balance with this one, in order for these conditions can be observed, we need more torque here, more moment here. That's why they add another 25 Newton load, right? Okay, so what missing here? That should be the difference between these two. Should it be 100 newtons centimeter, right? In order to balance these out. And this one should be the last force, the last moment from the 25 Newton loads. It also needs to multiply with D3. So can you find D3 now, which is now equals to 100 centimeter, right? Okay, easy now, just solve for D3. Then that should be this one divided by 25 Newton, which then equals to 4 centimeter, right? And then we can also say this one needs to have a counterclockwise moment. Okay, so where is it? Let's say this one is like 10, from here to here is 10, so middle of this is 5, so 4 is like somewhere here, right? That's 4 centimeter away from the pivot point. So this is where we should have the F3. So that 25 newtons should be placed somewhere here. Okay, and the final answer is 4 centimeter. Okay, let me know if you have any question. Good luck.